Howdy, howdy, this is Mr. Potter. The 2019 BC Calculus free response questions just came out, and so we're going to go ahead and work through them. So let's get started. So problem 1 says a fish enter a lake at a rate modeled by the function e given by e of t equals 20 plus 15 sine of pi t over 6. Fish leave the lake at a rate modeled by the function L given by L of t equals 4 plus 2 to the 0.1 t squared power. Both E of t and L of t are measured in fish per hour, and t is measured in hours since midnight. And part A says how many fish enter the lake over the 5-hour period from midnight t equals 0 to 5 a.m. t equals 5. Give your answer to the nearest whole number. Now what's interesting to know is that E of t is a rate. So if I want to find the number of fish, then I want to take the antiderivative of this, and I want to integrate this from 0 to 5. So I'm going to integrate from 0 to 5 of 20 plus 15 times the sine of pi t over 6. And I'm going to integrate that with respect to t. So I'm going to go to my calculator, and I'm going to integrate that. So I'm going to do integral of, it's going to be 20 plus 15 sine of, then I need pi t over 6, close the parentheses for sine. I'm going to integrate with respect to t, and I want to integrate from 0 to 5. And when I do that, I get this wonderfully horrible answer, my exact answer. But if I do green enter, then I should get an approximation of 153.458. Of course, keep in mind that I want to the nearest whole number, so this should be 153 fish. And of course, units are important, so let's use them. So that's part A. On part B, it says, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight t equals 0 to 5 a.m. t equals 5? And we have a formula for average value of a function. The idea here is that the average value is going to be equal 1 over b minus a times the integral from a to b of whatever my function is with respect to that variable. So in this case, I'm doing it from t equals 0 to t equals 5, and I'm dealing with L. So the average number of fish that leave is going to equal 1 over 5 minus 0 times the integral from 0 to 5 of L of t. This is this 4 plus 2 to the 0.1 t squared power with respect to t. So this is what I need to integrate. So I need to integrate 1 over 5 times the integral of, this is going to be 4 plus 2 raised to the 0.1 t squared power. When I integrate that with respect to t from 0 to 5, and to keep from making the same mistake I did before, I'm going to do green enter to get an approximate answer. And so my average number of fish would be 6.059. And keep in mind that this is the fish per hour, so this is going to be fish per hour. Again, units are very important for us. On to part C. Part C says at what time t for 0 less than t less than 8 is the greatest number of fish in the lake? Justify your answer. So I can say that the number of fish can be given by the formula, the number of fish that enter at a particular time minus the number of fish that leave after a particular time. So I need to figure this out. And where do critical points happen? Critical points are at where our derivative is equal to 0. So I need to figure out what this derivative is, and I need to figure out where it's equal to 0. So this is already a derivative because it is the rate modeled by the function. Similarly, L is a rate. So I really want to know, where is E of t equal to L of t? Because this is the place where I can have a critical value other than at t equals 0 and t equals 8, our boundary parts. So I'm going to go over here to algebra, which is F2, and I'm going to solve. And I want to know where e of t, so this 20 plus 15 times the sine of pi t over 6, and I want to know where that's equal to L of t, which is 4 plus 2 times, or excuse me, 2 raised to the 0.1 t squared. So that's my equation, and I want to solve for t. And so if I do green enter to get my answer, this should tell me approximation. Of course, it's going to tell me that more solutions may exist because I am dealing with a trig value. I need to find the solutions that fall in this 0 to 8 range. Come on, you can do it. So I get negative 6.61, bad answer. I get negative 4.09, that's a bad answer. I get t equals negative 2.4, and that's a bad answer. T equals 6.2035. That does lie between 0 and 8. So, E of t equals L of t when t equals 6.203 or 6.204. Either one of these would be fine. And of course, keep in mind that this is time, so this is hours. So after this many hours, this is where I'm going to have the greatest number of fish. And again, remember, anytime they ask us for a question, I need to answer it. This t equals 6.204 hours is where we have the greatest number of fish. Justifying my answer, that's where the number of fish entering equals the number of fish leaving. After that, this is a larger function. This is a smaller function. So that's part C. On to part D, it says, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m. t equals 5? Explain your reasoning. So if I find E of t, well, E of 5 is the number of fish entering, and L of 5 is the number of fish leaving. Remember, both of these are rates. So if I evaluate both of these at t equals 5, that's going to give me the rate of fish in the lake. And of course, if this is positive, then I'm going to be increasing. If this is negative, then I'm going to be decreasing. So I'm just going to evaluate this. So I'm going to put in parentheses. Let me go back down here and clear. I'm going to do parentheses E of t, which is 20 plus 15 times the sine of pi t over 6 minus L of t. So I need to make sure I subtract both of these. So minus 4 and minus 2 raised to the 0.1 t squared. And I want to evaluate this at t equals 5. What's wrong with that syntax? I think I've got double parentheses here. I think that's the problem. Let me fix that. And I get negative 3.294. So since E of 5 minus L of 5 is negative 3.294, which is less than 0, the rate is decreasing. So the thing is, I figured out the rate at the particular time, and I've explained my reasoning because this rate of change is less than 0. Anytime my rate of change is less than 0, I'm going to be decreasing. So this is problem 1. And on to problem 2. 2 says, let S be the region bounded by the graph of the polar curve r of theta equals 3 radical theta times the sine of theta squared for 0 less than theta less than the square root of pi, as shown in the figure above. Find the area of S. Now, we know for polar figures that I can find the area by integrating from theta 1 to theta 2 of 1/2 whatever r of theta is squared d theta. That's the formula for a polar area. And for us, we know the formula for r, and we know our initial and terminal theta. So our area is going to be the integral from 0 to square root of pi times 1/2, excuse me, not times, 1/2 3 radical theta sine of theta squared d theta. So I need to figure out this integral, and that's going to be my area. So I'm going to go over here and do the integral of, is going to be 1/2 times 3 times the square root of theta times the sine of theta squared, close for that, but I need to make sure that r, which starts here and ends here, gets squared as well. And I'm going to integrate this with respect to theta from 0 to the square root of pi. And when I evaluate this, I'm going to get an area of 3.534. So there's my area. That's part A. On part B, it says, what is the average distance from the origin, that's going to be here, to a point on the curve? So if I want to find the average distance, this distance here is r. So again, that's that 1 over b minus a times the integral from a to b of, in this case, it's going to be r of theta d theta. And I want to find the average distance from a to b. So it's going to be 1 over pi minus 0, square root of pi minus 0, times the integral from 0 to the square root of pi of r, which is going to be 3 radical theta times the sine of theta squared d theta. So I'm going to have 1 divided by square root of pi times the integral from 0 to pi of 3 times the square root of theta times the sine of theta squared. And I'm going to integrate that with respect to theta from 0 to square root of pi. Let me actually make that a pi in here. Close for the square root and close for the integration. We'll do green enter again to get approximate. And this is going to give us 1.5799 or 1.580. Both of these would be considered correct. So that's the average value. That's part B. On part C, it says there's a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. Write but do not solve an equation involving one or more integrals whose solution gives the value of m. Keep in mind that if I'm talking about a line with a slope of m is the change in y over the change in x, but we know that y over x is really tangent. So for us, m is really the tan inverse of some angle that we're making with the positive x-axis. So in other words, I can find m is the tangent of that angle. So theta, my theta, the angle, is actually going to be tan inverse of m. And what that means is that the integral from here to here that finds the area has to equal the integral from here to here. Now obviously I've misdrawn this line, but I need to make sure that I'm going to go from 0 to whatever this theta is, and then from theta to this square root of pi limit. And I want to make sure that these integrals are the same. So the integral from 0 to my value of the 1/2 r squared, 3 square root of theta, times the sine of theta squared, and this is going from 0 to tan inverse of m, has to be equal to the integral from tan inverse of m to the square root of pi of this exact same integrand, d theta. So 1/2 times 3 radical theta times the sine of theta squared, d theta. And what's nice about this write but do not solve is that all I have to do is write it out. I've got an equation, because I've set these equal to each other, involving one or more integrals. In this case, there's two integrals, whose solution gives the value of m. If I were to solve this, heaven forbid, I've got an variable, only one variable here, m. Because this is an integral from a constant value to another constant value, this is going to be constant except for m. This is going to be constant except for m. And so I'll end up with an equation that solely involves m. So that's part C. Finally, on part D, it says, for k is greater than 0, let A of k be the area of the portion of region S that is also inside the circle r equals k cosine theta. Keep in mind that k cosine theta is going to be a circle. It's going to be centered on the x-axis, and it has a diameter equal to k. So in other words, if k equals 1, it's just going to be a circle here with a radius of 1. If k equals 2, it's going to be a circle with twice the radius, but it's going to be centered on this x-axis. If k is 1,000, then this circle is going to go way up here and similarly come way down here. What I notice is that as k gets bigger and bigger, this place where it intersects is going further and further and further along the curve. Eventually, as k goes to infinity, I'm actually going to end up taking up the entire first quadrant and the entire fourth quadrant. So in other words, this area that overlaps between this circle that actually in reality takes up the entire first quadrant is going to be just everything in the first quadrant. In other words, stopping here at pi over 2. So my area is going to be the integral from 0 to pi over 2 of this 1/2 theta, 1/2 r squared d theta. So 3 radical theta times the sine of theta squared d theta. And so I just need to figure out what this is going to be. So I'm going to do 0.5 times the integral of 3 times the square root of theta times the sine of theta squared, and in this case r is being squared, and I'm integrating this with respect to theta from 0 to, now my upper bound is just going to be pi over 2. And of course, green enter to get an approximate answer. Going to take a bit. That's perfectly fine. We've got all day for the AP exam. So we get our area is 3.324. So that's how we find it. Again, we're using polars here, so this 1/2 r squared d theta, this area formula has been very prominent in here. But we've also had to take the relationships that we know between theta and slopes, or theta and other geometric figures, in order to answer these questions. So that's question 2. We no longer need our calculator, so we're going to move on from this point. All right, question 3 is often dealing with some type of graph that we're going to have to use geometry to find the antiderivative of. So here on number 3, it says the continuous function f is defined on the closed interval from -6 less than x less than 5. The figure above shows the portion of the graph of f consisting of 2 line segments and a quarter of a circle centered at the point 5, 3. And it's known that the point 3, and this is 3 minus radical 5, is on the graph of f. Part A says if the integral from -6 to 5 of f of x dx equals 7, find the value of the integral from -6 to -2. In other words, I have no idea what's happening to my graph out here when I go out to -6, but I know that the total area above and below has to come out to 7. And I know one of the properties of calculus is that the integral from -6 to 5 of a function is equal to the integral from -6 to 2 of that function plus the integral from -6 to -2 plus the integral from -2 to 5 of that function. And I happen to know that this is 7. This I don't know. This is actually what I'm trying to solve. this I can figure out using geometry. I've got a triangle with a height of 1 and a base of 1. So this is 1/2 base times height. This triangle has a base of 1 and a height of -1. So 1/2 base height. This triangle here has a base of a half and a height of -1, plus 1/2 times base times height. This triangle here has a base of 1/2 or 3/2 and a height of 3, plus 1/2 my base, which is 3/2 times my height, which is 3. Plus, and now I've got this region over here, which would be a square, but I've got to subtract this quarter of a circle. So this is going to be 9 minus 1/4 of pi times r squared. So all of this is my integral from -5 to 2. So if I want to find this integral, the integral from -6 to 2, all I have to do is take this 7 and subtract all of this. So this is going to be 1/2 times 1 times 1, and I'm not going to even bother doing calculations. I'm just going to copy these values down. Doing it correctly, of course. Plus, and I'm going to subtract this whole thing, 1/2 times 1 times -1, plus 1/2 times 1 times -1/2, plus 1/2 times 3/2 times 3, plus 9 minus 1/4 pi times 3 squared. And all of this is going to be subtracted from 7. And remember that this is a perfectly legitimate answer. I don't need to waste my time figuring out, oh, this is 1/2, this is -1/2, this is -1/4, this is +9/4. I don't need to do that, and there's no reason I should, because I may make a mistake doing it. If I leave it like this, as long as it's correct math, I should get full credit. And so this is part A. Moving on to part B, they want us to evaluate the integral from 3 to 5 of 2 times f prime of x plus 4 dx. Now keep in mind, this is going to be equal to the integral from 3 to 5 of 2f prime plus the integral from 3 to 5 of 4. Just the property of integrals here. And I can take this 2 and take it outside. And now I've got some stuff that's easy to evaluate. This is going to be 2 times the integral of f prime is going to be f. So it's really going to be f of 5 minus f of 3. And over here I've got a rectangle with a height of 4 and a base of 2, so this is just going to be 4 times 2. So now I need to figure out, okay, what is f of 5? According to my graph, f of 5 is 0. F of 3, well, luckily they told us f of 3 was this 3 minus radical 5 plus 4 times 2. And of course I can do more calculations if I want to, but this is a perfectly legitimate answer. So this is part B. Moving on to part C, it says the function g is given by g of x equals the integral from -2 to x of f of t dt. Find the absolute maximum of g on this interval from -2 to 5. Justify your answers. Keep in mind that absolute extrema happen at critical points and boundary points. So critical points are going to be where the derivative equals 0. F of t is the derivative of g of x. So where is f equal to 0? Well, here, here, and here. Those are the only places where f is equal to 0. And keep in mind, even though f has an undefined derivative at this point, f is 3 at this point. So I really don't want to say that x equals 2 is one of the critical points. And then, of course, I've got my boundary points here at -2 and at 5. So I need to check x equals -2, x equals -1, x equals 1/2, and x equals 5. Well, if I'm doing the integral from -2 to -2 of any function, that's 0. If I'm doing the integral from -2 to -1 of my function, that's really the area of this first triangle, which has a height of 1 and a base of 1. That's going to be 1/2 times 1 times 1. If I'm doing it from -2 to 1/2, that's going to have this triangle here and this triangle here. And these triangles really do cancel each other out. Geometrically, they're the same areas. Just one's above the x-axis and one's below the x-axis. So if I'm integrating f of t dt, that's a sideways t, all I'm really getting is just this negative triangle here with a base of 1/2 and a height of -1. So that's 1/2 times my base of 1/2 and my height of -1. And then the integral from -2 to 5 of f of t dt is all of that stuff that we wrote on part A, and I could copy that down. And of course, this is all coming from part A. But the thing is, this is actually greater than all of these. And so the absolute maximum of G is whatever this value happens to be. And because I've actually tested every possible extreme point, every possible critical point, every possible boundary point, I've excluded all the other possibles. And so the absolute maximum of G is going to be this triangle here cancels out. This is -1/4. This is positive 3/9/4, and all of that calculation that we have on part A. I could repeat it, but I'm not going to at this point. That's part C. Going on to part D, they want us to find the limit as x approaches 1 of, this looks horrible. And I'm thinking in my head, L'Hopital's rule, but you know what? I can only use L'Hopital's rule if this is indeterminate form. So let's evaluate at x equals 1 and see what happens. I'm going to have 10 to the first minus 3 times f prime of 1. Well, at 1, this is a line with a rise of 4 and a run of 2. So this is 4 over 2, which is 2, over f of 1. And f of 1 is 1 minus, I'm going to have the arctan of 1. Well, the arctangent of 1 is pi over 4, and this is not indeterminate form. So this is my answer. And of course, I could do a whole bunch of calculations here and evaluate what that comes out to. There's no reason for me to waste my time on that. So that's part 3. Problem 4 says a cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of height of the barrel is, with respect to time, is modeled by dH dt equals -110 radical h, where h is measured in feet and t is measured in seconds. And they give us the volume of a cylinder with radius r and height h is v equals pi r squared h. And I notice that my diameter is always 2 because it's a cylinder, which means my radius is always 1. So my volume as a function of h, and this is going to become important in here, is really pi times 1 squared times h, or just pi times h. This is my formula for volume. On part A, it says find the rate of change of the volume of water in the barrel with respect to time. When the height of the water is 4 feet, indicate units of measure. So I'm looking for the change in volume with respect to time, and I want to take the derivative of this with respect to time. So pi is a constant. It's not going to change if I take its derivative, if it's a coefficient. The derivative of h with respect to time is dH dt, which for me is going to be pi times -1/10 times the square root of h. And so dv dt at t equals 4 is going to be pi times -1/10 times the square root of 4. And I have to indicate units of measure. This is a change of volume. And volume here is being measured in cubic feet. And this is a change in volume over time. Time here is measured in seconds. So I need to make sure I have this value. And of course, I don't need to go through the calculation process. This is my answer. But I do need the units. I do need the cubic feet per second. So that's part A. On part B, it says when the height of the water is 3 feet, the rate of change in the height of water with respect to time, is it increasing or decreasing? I want to know if the rate is increasing or decreasing, which really means I want the second derivative of height with respect to time twice. So I want to take the derivative of this twice. Well, if I'm taking the derivative of h with respect to t, I get this. I want to take the derivative with respect to t of dh dt, which means I want to take the derivative with respect to t of this negative 1/10 radical h. Now I'm going to rewrite this as h to the 1/2 power because that makes taking the derivative a lot easier for me. Using the chain rule, of course, the 1/2 will pop out, so I have negative 1/10 times 1/2 times h to the negative 1/2 times dh dt because of the chain rule. So I end up with negative 1/10 times 1/2 times h to the negative 1/2 times dh dt, which is negative 1/10 times h to the 1/2. And what's really nice about this is that this part and this part eliminate each other. And so I'm left with negative 1/10 times 1/2 times negative 1/10. And that is positive. So the rate is increasing. And it's always increasing because the second derivative, my d squared h over dt squared, is always positive. So that's part B. Moving on to part C, it says at time t equals 0, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. So I know that dh dt equals negative 1/10 times h to the 1/2 power. And I'm going to use separation of variables, which means all of my independent variables are going to be on the right side. All my dependent variables are going to be on the left. So I'm going to have dh divided by h to the 1/2 power equals negative 1/10 dt. Or really, I've got h to the negative 1/2 dh equals negative 1/10 dt, and I want to integrate both sides. Now, integrating both sides, I'm going to have a constant of integration, which I'm always putting on the independent side because it's going to be easier for me to solve for h by itself. The integral of this is going to be h to the 1/2 divided by 1/2. The integral of a constant times dt is going to be that same constant times t. And so I need to solve for h. So I'm going to multiply everything times 1/2. So I've got h to the 1/2 equals 1/2 times negative 1/10 t plus a constant. But this is really just 1/20 t plus some other constant. And that's h to the 1/2 power, so h is going to be this squared. So negative 1/20 t plus a constant squared. So now I need to use this last bit of information. At time t equals 0, the height of the water is 5 feet. So if t is 0, when I square that, I should get 5. And so I find out that c equals the square root of 5. And so my formula h of t is going to be negative 1/20 t plus the square root of 5 quantity squared. So I've solved my differential equation, and of course the 5 main points is the separation of variables, integrating both sides, remembering your constant of integration, solving for your dependent variable, and then solving for your constant. Those are always the big points that they're looking for when you've got a differential equation. And so that's problem 4. Moving on to problem 5, it says consider the family of functions f of x equals 1 over x squared minus 2x plus k, where k is a constant. And it says find the value of k for k greater than 0 such that the slope of the line tangent to the graph of f at x equals 0 equals 6. So for us, I want to find k when the derivative of this equals 6. So really f of x for my purposes is x squared minus 2x plus k to the negative 1 power. And so the derivative of that is going to be negative 1 times x squared minus 2x plus k to the negative 2. And the chain rule is going to give me 2x minus 2. And I want to know when is this equal to 6. And of course, I'm saying if x is equal to 0, so this is going to be negative 1 times 0 minus 0 plus k, so this is going to be k to the negative 2, times this is going to be 0 minus 2, so this is negative 2, equals 6. So I've really got 2 over k squared equals 6, or 2 equals 6k squared, or k squared equals 2 over 6, and k is the principal square root, 2 over 6. Now I could say it's the square root of 1/3. No reason to do so. You can do it if you want to. You don't get extra points if you do the math. You just lose points if you do it wrong. So that's part A. Moving on to part B. Part B says for k equals negative 8, find the value of the integral from 0 to 1 of f of x dx. So for us now, f of x is really equal to 1 over x squared minus 2x plus 8. And in order to evaluate the integral of this, I'm going to need to write this as partial fractions. One of the things that I notice is that this does factor to x squared minus, or excuse me, to x minus 4 and x plus 2. So this is going to be something over x minus 4 and something else over x plus 2. So I need to solve for a and b so that I can actually have two separate integrals that I can integrate easily with natural log. So I know that a over x minus 4 plus b over x plus 2 has to equal 1 over x squared minus 2x plus 8. And if I cross multiply, I end up with 8x plus 2a plus bx minus 4b equals, in the numerator over here, I'm going to have 0x plus 1, which means all of my x's have to add up to 0, and all of my constants minus 4b equals 1. Of course, this is not going to help as much as this will, because over here I can say that, here I could say that a equals negative b, and that means that wherever I see a negative b, I can replace it with a, so I end up with 2a plus 4a equals 1, so a equals 1/6, and b has to be the opposite of that, so b has to be negative 1/6. So going through this integral here, if I want to integrate from 0 to 1, this 1 over x squared minus 2x plus 8 dx, I can write this as the integral of 1/6 1 over x minus 4 dx plus the integral of negative 1/6 1 over x plus 2 dx. And I'm integrating each of these from 0 to 1. So this is going to be 1/6 times the natural log of x minus 4, which I'm evaluating from x equals 0 to x equals 1. And this is going to be negative 1/6 times the natural log of x plus 2, which I'm evaluating from x equals 0 to x equals 1. So substituting 1 minus 4 is 3. This is the absolute value of negative 3, so I'm going to have 1/6 natural log of 3. Minus, substituting a 0, this is going to be 1/6 natural log of 4. Over here, this is going to be minus 1/6 natural log of 1 plus 2 is 3. And then substituting 0, I'm going to have plus 1/6 natural log of 2. And of course, this is a beautiful answer. If you want to, you could eliminate that pair and just end up with 1/6 natural log 2 minus 1/6 natural log of 4. I could make this 2 squared, bring the 2 on the outside, and end up with negative 1/6 natural log of 2. I'm not going to get any extra points for simplifying my answer as I would from getting this answer here. But if I make any mistakes along the way, I'm going to lose points. So please be careful when you're doing this math. So that's part B. Moving on to part C, it says for k equals 1, find the value of the integral from 0 to 2 of f of x, or show that it diverges. This is important because for us, f of x is 1 over x squared minus 2x plus 1, or 1 over x minus 1 squared. And the value of x equals 1 is not in the domain of my function. The question is, does the integral exist or does it diverge? So if I want to evaluate this integral, I really want to evaluate the integral from 0 to a as a approaches 1 from the left of x minus 1 to the negative 2 dx. Plus, I want to do the integral from b to 2 using the limit as b approaches 1 from the right of x minus 1 to the negative 2 dx. So I need to treat these as improper integrals because the value x equals 1 is not in the domain of my function 1 over x minus 1 squared. Integrating this is fairly straightforward. That's going to be x minus 1 to the negative 1 over negative 1. And I want to evaluate this from x equals 0 to x equals a, again with the limit as a approaches 1 from the left. And I want to do this. This is also going to be x minus 1 to the negative 1 over negative 1. And I'm evaluating from x equals b to x equals 2, taking the limit as b approaches 1 from the right. So if I take a look at what I've got here, I'm going to have, substituting in, that's going to be a minus 1, the reciprocal negative. So it's going to be negative 1 over a minus 1. The limit as a approaches 1 from the left, minus, substituting a 0, this is just going to be negative 1 over negative 1, plus, now I'm going to evaluate this, evaluating at 2, this is going to be 2 minus 1, which is 1 to the negative 1. So I'm going to have negative 1 over 1, minus the limit as b approaches 1 from the right, substituting b in here, this is going to be b minus 1, that's in the denominator, and negative 1 here. So this is going to be negative 1 over b minus 1. And what I notice here is that this and this really are the same thing. I mean, they are equal in magnitude, opposite in direction. They kind of cancel each other out. And I can't just leave them in here because there's still calculus to be done. But what I'm left here is I'm left with negative 1 and negative 1, so I really end up with negative 2 as an answer. And so choice C, the answer is negative 2. So that's 5C, and that's problem 5. All right, moving on to 6, moving on to our Taylor and Maclaurin series problem. It says a function f has derivatives on all orders for all real numbers x. A portion of the graph of f is shown above, along with the line tangent to the graph at f at x equals 0. Selective derivatives of f at x equals 0 are given in the table above. So I've got this table. This is the second derivative, the third derivative, the fourth derivative. But keep in mind, if I need a Taylor polynomial, I really need to know what the first derivative is, as well as what the value of the function is. And that's the purpose of this graph. At x equals 0, I'm passing through the point 0, 3. And at x equals 0, my slope is going to be this line here, which goes down 3. Actually, it goes down 2 and over 1. So that would be a slope of negative 2. So my first derivative is negative 2. And now I'm ready to write a third degree Taylor polynomial. So T3 of x, my third degree Taylor polynomial. Remember that Taylor polynomials are the sum from n equals 0 to infinity of the nth derivative at a times x minus a to the n over n factorial. For us, a is 0, which makes this really nice because I'm just going to use the values from this table. And I'm going to have to use the values of n from 0 to, for our purposes, 3. So I'm going to have the function itself. So this is going to be 3x to the 0 over 0 factorial minus 2x to the first over 1 factorial plus 3x squared over 2 factorial minus 23 halves x cubed over 3 factorial. Now, can I write 3 factorial as 6? Sure. Can I simplify the fraction so it's 23 over 12? Sure. Do I want to make that mistake? No. So this is my third degree Taylor polynomial. Moving on to part B. Part B says write the first 3 non-zero terms of the Maclaurin series for e to the x, and then write the second degree Taylor polynomial for e to the x times f of x about x equals 0. So we know that e to the x is equal to the sum of x to the n over n factorial. So the first three non-zero terms of the Maclaurin series, so ME of x, would be equal to 1 plus x squared. That would be the first three non-zero terms of the Maclaurin series. And then I have to write the second degree Taylor polynomial. If I'm going to do the second degree Taylor polynomial, I need to know what my function, let's call it g. So g of x is e to the x times f of x. So g of 0 is going to be e to the 0 times f of 0, which is 1 times 3, or 3. G prime of 0, well, this is a product, so I'm going to have the first times the derivative of the second, e to the x times f prime of x, plus the second times the derivative of the first, but the derivative of e to the x is e to the x. So this is really going to be 1 times the derivative, which was negative 2, plus the function, which is 3, times e to the x, which is 1. And then I need to do the same thing with g double prime of 0, which means I need to take this derivative again. And again, I've got product rules here. So I'm going to have first times the derivative of the second, plus the second times the derivative of the first. And then same thing here. First times the derivative of the second, plus the second times the derivative of the first. So I'm going to have 1 times 3, according to the table, plus this was negative 2 times 1, plus this is 3 times 1, plus 1 times negative 2. So I've got g, g prime, and g double prime. I'm ready to do the second degree Taylor series here by using these values. So I have 3 x to the 0 over 0 factorial, plus this is really negative 2 and 3, so this is negative 2 plus 3 x to the first over 1 factorial, plus I've got this 1 times 3 plus negative 2 times 1 plus 3 times 1 plus 1 times negative 2 x squared over 2 factorial. Again, no reason for me to make a stupid math mistake if it's going to cause me to lose points. So that's part B. On to part C, it says let h be the function defined by h of x equals the integral from 0 to x of f of t dt. Use the Taylor polynomial found in part A to find an approximation for h of 1. So we know from f of x in part A, we said that that was equal to 3 minus 2x plus 3 halves x squared minus, what was that, 23 over 2 x cubed over 3 factorial. Would that come out to? So if this is f of x, I want to integrate that to find the Taylor polynomial to find an approximation for h of 1. So h of x should be the integral of this. So that would be 3x minus 2x squared over 2 plus 3x cubed over 2 times 3 minus 23 halves x to the 4th over 4 times 1 over 3 factorial. And now I want to evaluate this at 1. So it's going to be 3 times 1 minus 2 times 1 over 2 plus 3 times 1 over 2 times 3 minus 23 halves times 1 over 4 times 1 over 3 factorial. Perfectly legitimate answer. All I'm doing is I'm substituting x equals 1. So that makes my life fairly easy. That's part C. Finishing this up on part D, it says, it is known that the Maclaurin series for h converges to h of x for all real numbers x. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. This is important because this means that I do have the absolute series test making this converge. So we have the alternating series error bound, and we know that our error is always going to be less than the absolute value of whatever the next term is. So for us, I need to figure out what the next term is for that previous problem. That was dealing with this term. So I know that my f sub 4 term would be 54x to the 4th over 4 factorial. That's for f. For h, it's got to be the integral of this. So that's going to be 54x to the 5th over 5 times 4 factorial. And I want to make sure that it differs from h of 1 by at most 0.45. So for us, our next term is going to be 54 times 1 over 5 times 4 factorial. And I need to kind of do a little bit of math here because I need to compare it with 0.45, and it's not necessarily obvious here. But what I've got here is I've got 54 over 5 times 4 times 3 times 2 times 1. I know that 2 goes into that 27 times. I know 3 goes into that 9 times. So I really have 9 over 20. And I do know that 9 over 20 is 0.45. So I can do a little bit of math. I have to do a little bit of math here to show the relationship between this next Taylor coefficient and the value that they gave me here. All in all, I felt that this was a pretty straightforward free response. There were a couple of little tricksy stuff, but I didn't think it was overall that difficult. I thought that it's very similar to the problems that we've seen. And one of the things that we know that's coming up in the 2019-2020 testing year is that they're really going to standardize these free response tests a lot more. So we'll know exactly what to expect, and they've kind of been laying the foundation for this. We've known for a while that problem 6 is going to be a free response question. We've known for a while that problem 3 tends to have either a graph or a table, and we have to use that to extrapolate data. We know that problem 2 always seems to be either a parametric or a vector or a polar equation. And so there's a certain pattern that we notice, a certain pattern that we got that comes out of this. And we're going to see that pattern reinforced in the future. I certainly believe so. Once again, this is Mr. Potter. Thank you for watching. Have a great day.